you have an animation and you actually want to change the timing of that animation, or you want to change some poses and kind of offset the animations as if it was an animation layer. This is the kind of functions we take for granted in all our 3D animation package and even in most of our game engines. But once upon a time, it was actually a paper. Hi, I'm Jerome, and today we'll be looking at the motion warping paper from 1995. The motion warping paper takes as idea that you actually have a bunch of curves that represent the animation, and it would treat all of those curves separately, and then from there you could actually change those curves to tweak your animation. So let's see how it was done and how we could implement this in NumPy. So basically I will import, as usual, all my libraries and my viewer, and I will import my character and I will duplicate it so I get several characters, so I can render several characters back to next to each other. That will make my life easier when I would want to show different options. Then what I would do is actually just load one animation, and I will load the Fight and Sport animation from the LaFan animation set. And from this animation, what I would do is that I will extract two different poses at the end of the animation. So see, I'm taking a pose A at frame 695 and one at nearly 2000 frames. And then I will only use a small range of the animation, so only 500 frames of animations that I'm interested in inside of this bigger animation. So this is the animation I've kept. And so what you could see is just basically a guy dancing on one foot and giving some kicks on one side and then coming back on the other side. So that's the animation I will use, and that's what I want to tweak, where I want to change the timing and I want to change the pose and all that kind of stuff. So just to represent the fact that the paper is talking about a bunch of curves, I would display here one of the numerous curves that I have on the characters. So basically I'm picking the quaternions of the left up leg of this character, and you could see, so that's the four different values, scalar of that quaternion. So I get my W, X, Y, Z. So already just one rotation is four different curves for one bone, and then I have that for all the bones. And so what the paper is basically saying is that you could warp your animation using two different functions, and the two different functions that they do, so they warp the motion curves with defined by two functions. And basically what they said is they said that the new curve will be a function of t, and that function of t, that new curve will be a functions of the original functions at time t. And then they also say that the time t is defined as a function of the original times. So they warp t prime to t in that order. Basically what they say in this paper, they say that it's easier to say my new animation will have frames that go from 0 to 100, for instance, and I will want to map frame 0 with the original frame 50, for instance, with frame 60 of my original animation, and frame 100 might be frame 200 of my original animation. So that's the functions they want to do to map the time differently, and then they have the functions to map the pose differently. I will start from the timing function because it's easier to assume only one dimension, let's say. And what they said inside of the paper is that basically you give a bunch of keyframes saying that's the time inside of my animation, that's the time inside of my old animation. And you need a functions a smooth functions to interpolate those values. And the smooth function they use is the cardinal spline. They basically says that you could use any type of spline, but they went for the cardinal spline, so I will do the same. I will use the cardinal spline. So what I have is as in the paper, I basically have new time, old time keyframes. So at frame 0, I want to be at frame 0 inside my old animation. At 40, at 100, I want to be at frame 190. So I want to speed up quite a lot, and then I will slow it back down, saying that at the end, at frame 430, I will only be at frame 400 inside of the animation. So I will not even reach the end of the animation with my new animation. So that's the keyframes I will have. And basically, I picked the functions from the spline theory papers that videos have made. So I will just reuse the same functions. So that the one that converts a cardinal spline to Hermit, and then how to compute an Hermit spline. So I will have the Hermit functions that I can directly use to do my mapping. And now, basically what I would do is just use the Hermit functions to convert the different points into a curve, so we could see what is the mapping I actually want to do for the timing. And so this is the mapping I have. So basically, that's the new keyframes I will be generating for my animation. So from frame 0 to frame 430. And then we can see the corresponding frame I will go and pick inside of the original animation. So I will have at frame 0, I will be picking the frame 0. At frame 100, see nearly at frame 200. That's what I was saying. 200, we are on 250s, and so on and so on. So that's the mapping that the curves allows me to have between my new frames and my old frames. The only issue I have with this kind of curves that every time I will want to request the values at a specific frame for my new animation, I will have to go and find the correct corresponding values inside of the Hermit curve to find where I'm supposed to be here and then where I will be at the end. So it's not really user-friendly to use the Hermit curve directly this way. And what I will do is that I will resample this Hermit curve now for every frame down here. So basically, I would say now I know that between this point and the other points that I put here at frame 100, I have 100 frames. So I will compute 100 different values. So I get a perfect mapping and so on for every point along my entire curve. So that's what the resampling is doing here. So it resamples a curve that you give him. So it will give you as many frames as the frames you were supposed to get here. So that's the resample functions. And to show you what it means to take this Hermit curve and regenerate a new curve using that resample, basically gives me this now. I still have the curves as it was designed, but now I have for every keyframe in my new animation, I have a direct mapping to where I want to be in the old one. So I don't have to compute anything down here now anymore. I can just say, hey, I'm computing frame 1. What is the value? I'm computing frame 10. What is the value? And so on and so on. So it's basically becoming a big lookup table, which makes my life easier when I want to execute more code after that. So now that I know that I want to be able to compute this kind of curves with a linear spacing for all my functions, for all my frames, basically I will write those functions so I can reuse them. And that's what those two functions are. They have the build curve is the one that generates these curves. Basically saying, if you give me a bunch of keyframes that are going onto an Hermit, I will resample that values to give you now a mapping between for every frames and that values. So that's what the build curve does. So it creates this mapping. And then the warp curve is actually the real functions now. Is the one that you want to use if you want to warp a data using that that curve you generated here. So the time warp, it tells you what is the data for every frame. And this one allows you to go into that curve and modify the curve. So basically, the only thing it does, it looks inside a curve So if the time warp said you're supposed to look at frame 10, it goes inside of the curve and looks at the value for that frame 10 and so on. But then it will do a linear interpolation between two frames. And why is it doing that linear interpolation? Is because now, for instance, at frame 1 at 300, it might tell me that the value here is not a round frame. It might not be 300, it might be 300.5. So I do need to do the linear interpolation between frame 200 and frame 201. So that's what the warp curve does. It goes and it picks the two closest frame and do the linear interpolation between the two, and it does it on the entire curve at once, on the and any dimensions, but the entire curves at once. Let's remember this one. So that's the two functions I will be reusing every time I try to build a curve, or every time I try to warp a curve using a time warp. And then we could do finally that time warp now. Basically, I can use my build curve to create the warping curve, that blue one. And then I could use the warp curve to go and look at all the quaternions of my animations and warp all those curves using the time warps curve. So as I said, this function is able to do it on the entire animations, but as in any dimension. So basically, it can do it for every bones of the W, X, Y, Z of each quaternions. So it does it in one pass. So it modifies every curves, which means that now I need to normalize those curves, because what happens is that I'm not using a slope here between the quaternions. I'm just warping every curve separately. So I'm basically breaking the rule that says that my quaternions need to be a unit quaternion. So I need to renormalize them. So I renormalize all my quaternions, and then I compute the new curves also for the positions using the warp curves function. And so we can display the results, and basically what you will see is that the white one is playing the normal animation, and the green one plays the warped animation. You could see that at the beginning it was speeding up a lot, and now it's slowing down to reach that point at the same time as him. It does not even reach the end of the animation. So that's what the time warp was supposed to do. So basically accelerate, because I wanted to be at frame 100. I wanted him to be already at the same position as frame 190. And then at frame 350, they had to be back together at the same time. And then it was slowing down to reach frame 400 at frame 430. So that's the timing change of the warping functions. So I have the functions that allow me to map a value to another one. And in this case, the value that I map to another one is the time. And now what we want to do is actually do the pose change. So do the first part of those functions here, that the one that we have here, that says that we change the curve based on functions that would change the curves itself. And what I will do is, again, I will do keyframes. So I will have the frames for which I want to change the values. Those frames are in the original timing. And for all of those frames, I will actually give a pose that I want to match at that time. So basically at frame 0, what I would say is that I want to have frame 0. So basically frame 0 means at frame 0 I want the same pose as the pose that you already have. Then at frame 190, I want the pose A that I extracted at the beginning, remember. Then frame 2 and 20 and 3 and 20, I actually want the animation itself. And then at frame 349, I want the pose B that I extracted earlier. And then again, the 2 frames coming from the animation itself. So that's the keyframes I want to generate. So basically, it's really as if I was doing in 3D software. I'm doing a layer on top of my animations, and that's the pose I want to put on that layer. And to show you all the different stuff that but I'm trying, if I don't execute that, of course, I will not have my keyframes. And so if I show you this, so this is the animation that is playing. And what I said is that at frame 190, I think, is that the one? Yep. At frame 190, that would be this pose in the original animation. And actually, I would want this pose to be visible instead. So I want to modify this pose to be this one at frame 190. And then at frame 350 something, 49, 50, when it reaches this pose, instead of having his leg completely stretched, I want this pose here. So basically I want to remove entirely the fact that he lifts the legs up. So that's the two pose that I want to change in the layer. And then everything else, I want him to play the normal animation with the ease in and ease out, because I have from frame 0s up to frame 200 something. Here in the middle, that should be again the normal pose, and at the end also. So that's what I want to do. To do this, what they do in the paper is that they treat every curve as just curve, and they do the mathematics on top. They just do minus and add. What I would do in my case is, knowing that I'm actually working with quaternions, so instead of directly just working on each curves and computing offsets on the curves, I will actually compute offsets in the quaternion space directly. So what I will do is that I will multiply all my keyframes that I have here, all those values, keyframes, I will convert them into an offset compared to the actual animations that I want to apply. So I will multiply the inverse of all of my animations with the keyframes. So that gives me an offset, that gives me how much I want to modify the original pose compared to with the pose I have. And if so this is what I compute here. So I turn every keyframes as offsets. And now basically what I could do is that I could use that same functions that I had to map the timing from the original, from my new timing to the original timing. I will use that to map my local offsets inside of the actual new timing I want to do. So I will build a curve that will give me the amount of offsets I want to apply on every frame. So this is what I'm doing. So I'm basically going through a build curve, and I will build that curve separately for each WXYZ of my quaternions and each XYZ of my position. So I need to compute that separately for each curve. And basically, if I display one of the curve you end up with is this one, you could see that you get a quaternion at frame 0, 0. At frame 0, that will be the identity. So I mean, I don't want to change anything. And then at frame 190, that's where my big change happened. And then get the identity again, no change, the big change, and so on. So, and that's the same for every different bones I have inside of my system. So that curve is already the amount of offset I want to apply on every bones along the animation. So I could display that change directly to show you basically what it means now, using just the position warp, or the pose warps. And so basically you could see that it's already rotating the head because it knows that it would reach, if I go back, it would reach at frame 190. That's the pose I wanted him to be, and that's where I want him to be now, which is the case. And it's already slowly applying that change along from frame 0 up to there, slowly applying that change. And then quickly goes back in the right pose. And at the end, it will also start to not kick because it's framing. And then because it holds the kick a long time, it's starting to slowly catching up. So that's the change in the pose that I wanted to do, basically as offsets compared to what animation is. And then the final step to complete the paper is to combine both, to say that you want to change the pose and you want to change the timing, by saying that instead of looking at the change in pose inside of the old timing, you will do it in the new timing. So you would basically do the same. You would change the timing and change the pose. So what I'm doing is that I take the curves, the offsets I've applied here, I take that new curve that does all the change, and I also warp it in using the time, and so I can have now something related to the new time with the new pose. And you get this. So the green guy will be playing just the retiming, and the blue one will be playing the retiming plus the change in the pose. And that's what the motion warping paper was all about. And as I said, it's something that we take for granted in all our software, but it's always interesting to see how it could be computed and all the curves that are in the background to compute that kind of stuff. It will be used in a lot of different papers after this one, because most of the time you will want to change timing, we want to change pose, we want to reach some stuff, and every single time it's basically this or something close to this that will be used. Hope you enjoyed it, and see you next time.